Okay, our next speaker is Suzanne Hibbs. She is currently a senior R&D scientist at Sigma Aldrich, where she utilizes cutting-edge technology to develop custom cell lines in the cell design studio team. Her talk, Advances in Cell Line Engineering, will detail a summary of efforts that have enabled clone identification in a polyploid cell line when homologous recombination is inefficient.
Hello, good afternoon. Thank you for having me today. As Doug said, I'm a scientist in the cell design studio team. We specialize in cell line engineering, and as such, we have acquired a wealth of knowledge in the cell line engineering workflow. And in my talk today, I would like to share some of that knowledge with you, and then follow that with 2 case study examples that demonstrate some of the tools and molecular biology techniques that can be used to identify genetic lesions. In the first example, we have created a SNP mutation on all 4 copies of a target gene. In the second example, we have a case where the frequency of the desired modification was around a range of 1 in 50,000, and this presented a particular challenge to find those clones. So first, I'd like to tell you a little bit about our group. We specialize in engineering mammalian cell lines. Our group was founded in 2007. We've engineered hundreds of cell lines, including stem cells and also many other immortalized and transformed lines. We use 3 key technologies: shRNA for the gene knockdown, and then also both CRISPR and TFN for genomic editing. The main point is that we have extensive expertise, and we like to talk with our potential clients and discuss their particular needs. We have the knowledge and experience to do this work. However, if you decide to embark on this project yourself, this chart provides an overview of the cell line engineering workflow. It doesn't seem too onerous to follow a simple flow chart. However, there are many things that can go wrong. Hopefully I can give you a description of some of the things that you want to consider when starting an engineering project. So when you have your cells of interest and your selected technology, you will nucleoffect or transfect the cells in some way. However, you may find that you don't have an optimized transfection protocol, and so you'll have to develop that. And then once you've transfected, you'll want to verify that your nucleus has cut the target gene using an assay such as cell line. And then at this point, you'll need to decide if you will plate the cells in small pools or go ahead and single cell clone. And if you decide that you need to start with pools, you'll need a genetic analysis to find the mutation of interest, and you may find that that method isn't sensitive enough to detect the pools. So hopefully you'll get that far, and then you'll get to single cell cloning. However, many cell types do not clone at a very high efficiency. And then eventually, when you do find the cell that you're interested in, you may notice that the cell characteristics are not what you would have expected. And then finally, when you get through all of that, you can actually do the experiment that you set out to do at the beginning. Okay, so now I'm going to focus on just one part of the workflow, and that is screening strategies. So when you're trying to reduce a SNP mutation, a couple of the techniques that you could use is RFLIP, or digital PCR, which I'll describe in my case studies. If you're looking at frame shift mutation or any type of mutation which adds or deletes nucleotides, we prefer to look at amplicon length change by amplifying the genetic lesion with labeled primers and then running that amplicon through a capillary sequencer to actually measure the length of the amplicon. If you're introducing a phenotypic change, such as a loss of epitope, this can be used as a method to screen. And then in the case when you're introducing a fluorescent marker, just the expression of that fluorescent protein is also a very good way to screen. The main message is that the method that you select to screen your cells is dependent on the type of change that you're trying to introduce and the frequency with which you expect to find that change. So in the first case study, we were introducing a SNP mutation in a tetraploid cell line. And we were using the CRISPR paired nuclease technology, and we were using a single-stranded oligo donor. So in this case, we decided that ARCLET would be an appropriate strategy. And this is a good strategy to use if you are able to insert or ablate a restriction site. We knew that the CRISPR paired nuclease cut at a high efficiency. However, the high efficiency cutting did not translate to a high efficiency of homologous recombination. So we started out with 100 cell per well pool, so that amounted to about 19,000 cells. And of those, 25 pools were positive for digestion with the restriction enzyme BAN2, as you can see in the lanes that have the expected size digest product. So we carried those pools forward and seeded at 10 cells per well. At the 10 cell per well stage, we found 12 that were positive for digestion, and carried those forward to the single cell stage. And finally, we found 7 out of 72 had the SNP introduced on all 4 alleles, and the wild type band is no longer present, only the digest products indicating the presence of the SNP. So how can you improve your chance for success in a case like this? Well, you might be able to introduce a silent mutation. We know that oftentimes the nuclease will retarget the site even if you've already introduced your desired mutation. So by introducing a silent mutation, you can prevent this retargeting. But this is also an important strategy to use when you need to introduce a restriction site where one doesn't already exist. And the example I showed you, the introduction of the SNP created that restriction site, but that's not always the case. So this silent mutation is also a way to add that restriction site. And this was an appropriate method for us to use because we knew that we needed to screen a lot of cells in small pools, and we knew that this would be sensitive enough to find the mutation that we were looking for. And it was also help us to find cells that had complete conversion on all 4 alleles, which doesn't happen at a very high frequency. But we do know that cell lines will vary widely in the rate of homologous recombination. In the second case study, we were looking for something which I really consider to be a rare find. And I sort of liken finding modified cells sort of to like finding a needle in a haystack. And many times we're asked, how many cells do you need to screen to find the modification that you're looking for? Or if I decide to use a small pool strategy, how many mini haystacks should I make in order to find what I'm looking for? So we've recently started using digital PCR to answer some of those questions. Digital PCR is basically the partitioning of one qPCR reaction into thousands of microreactors. And why is this useful? It's useful because in qPCR, when you have one reaction with an abundant wild-type template and then a rare mutation, you will not detect that rare mutation above the wild-type background. But with digital PCR, because you compartmentalize that template into its own microreactor, it can be detected and quantified. So there's several different instruments that are available on the market for doing digital PCR. We are using Bio-Rad's droplet digital PCR instrument. We selected this instrument because the sensitivity, which is one of the number of partitions. In this case, it's about 10 to 20,000 partitions. And we find that this level of sensitivity is just right for the type of work that we're doing. So I know that Dr. Suzanne is going to be speaking right after me, and he's from Bio-Rad, so he'll be going into a lot more depth on this instrument. But in brief, the way that it works is to prepare the PCR reactions, generate the droplets with the droplet generator device, and then run the PCR in the standard film cycler and then move the plate over to the droplet reader device, which then reads each droplet as positive or negative for one or both detection probes. And then those are plotted, and the data can be analyzed. So in my case study, following nucleoinfection, we decided that we would plate 5,000 cell per well pools. And then we would screen those pools with the digital PCR, and then replay positive pools with fewer cells guided by the calculated frequency until we would finally be able to find the clone that we were looking for. So we started with 35 pools of 5,000 cells per well. So that amounts to about 175,000 cells that we were looking at. And at this level, we were able to detect phantom-positive droplets. Those droplets are in the upper left quadrant, while in the upper right quadrant are droplets that are positive for both detection probes. And then on the x-axis is droplets that are positive for the wild type. So at the 5,000 cell per well level, we were able to detect phantom-positive droplets, but there were still too few copies to quantitate. So then we looked at pools at 100 cells per well, and we found the ratio was about 1 to 200. So we expected about 1 out of 200 of those templates was our SNP. So then we plated those positive pools at 10 cells per well, and came up with a ratio of about 1 in 30. So as we moved up, we did a series of 3 steps of subpooling. And eventually we were able to find 4 unique clones out of what we started with nearly 200,000. So that was very difficult and very rare to find. And how can we improve our chance for success? Well, one idea might be to introduce a selection marker. In some cases, this may not be desirable. We are able to find the clones without using that, but it is a possibility to increase the number. And then one other point that I wanted to bring up was that in this case we were looking at a ratio of SNP to wild type, and we knew that our cells had 3 copies of the gene to start out with. And so when we were looking at a ratio of the SNP to wild type, we came up with a ratio of 1 to 1. And we were trying to answer the question in this heterozygous clones, how many alleles have been converted? And if we wanted to go back and retarget that cell to capture all alleles, how many alleles remain wild type that we need to modify? And when we got a ratio of 1 to 1, that was surprising since there's supposed to be 3 copies. At least there was when we started out. So we used primers that were stepped out further from the genetic lesion. And from that, we could see that there was a large deletion that presumably removed a primer binding site. So this seems sort of obvious to me looking at it now, but I pointed out because it's not obvious if you weren't looking for it. If you weren't measuring your copy number at the beginning and the end of the project, you might not even know something like this has occurred. So I just wanted to try to point out some of the nuts and bolts and the things that go into designing and executing a cell line engineering project, things that you may or may not have considered. And another point that we often run up against is that the gene or the mutation that we're targeting leads to a proliferative disadvantage, which makes it even less frequent to find the cell that we're interested in finding. So there's just many issues that can come up amongst a lot of the obstacles that we have to deal with. One of them is the screening methodology. And this is only a few of the methods that we have used, but I hope it's giving you some idea of the things that go into each project. And then I wanted to sum up by showing you all the people that go into making this possible. As you can tell, we have a sizable tech team, but we also have several other groups that work together in coordination with us, including a bioinformatics team that delivers the high-quality reagents to us, and then also dedicated project management that manage each step along the way. I'll be happy to take any questions. Yes.
So workflow outlining from the transfection to the final cell selection, right? So what you can see that if you really the best way to shrink that workload is to increase upstream the targeting efficiency, right? So have you tried, for example, now the increasing the available mRNA or protein-based type of intake of the material, so that it would decrease the baseline lifetime of the cells, would decrease the chance of retargeting the locals. So that's like, are you trying those with new way of delivering the baseline sgRNA into the cells?
Yeah, so oftentimes the issue is not with delivery. We are getting high efficiency delivery. We're getting high efficiency of double-stranded break, but we're still seeing low rates of homologous recombination. And we are investigating ways in which we can sort of hedge our bets towards homologous recombination, but I don't have that data to show you today.
Yeah, can I just follow up on that? Because we see the messenger RNA and all the play is the ratio. You can increase the amount of the template plus cells to increase your HDR.
Yes.
So Suzanne, the senator mentioned in her talk that selecting the right sgRNA is empirical. I would imagine that sigma, just the sheer numbers of sgRNAs that you're either using internally for projects or providing externally to customers who want to do their own projects, that there could be some critical mass of data that's accumulating to help refine that process so that it's not so empirical. Is that something that the bioinformatics team is taking on as a challenge?
Definitely, definitely. Our bioinformatics and CRISPR R&D team are working to provide the latest iterations of design and what has worked and what has not worked. I will tell you from my own experience that there is still an empirical nature to it, and that we find different results with different cell types. We find that while one guide may work with one cell type, we will put that same guide in another cell and it doesn't work. And we also prefer to use the paired nickase technology wherever possible. And sometimes we'll find that guides will cut with wild type Cas9 singly, but when we put them in pairs in coordination with each other, it doesn't work. Or it does work in one cell type, but not in another. So unfortunately, there still is a lot of empirical work.
Thank you, Suzanne.